Hello, everyone. Good morning and welcome to the second day of this workshop. Uh, I will just let Gaurav take charge. Over to you, Gaurav.
All right. Thanks, Jatin. All right. So, we're going to talk about policy gradient methods today, but there was some stuff that I wanted to talk about yesterday that I didn't get to talk about. So I'm going to start with that. But before we do that, just let's talk about what we talked about last week, or sorry, yesterday, right? Um, okay, so we have MDPs that are formalizing our RL problem, and they're described by some fixed initial state, right? Some horizon. Um, and the two main aspects of MDP are this transition function and reward functions. And these are going to be the functions that we'll be focusing on most. Like the other stuff is we're using as just parameters, right? So we need to focus on transition function and reward function. And transition function is this function which tells us if you're in a state S, you take action A, what's the distribution of your next state? Okay, and reward function is saying, if you're in state S, you take action A, what's the distribution of your reward? So these seems like pretty important for a game. So, and these are basically going to be enough for us. And another thing we need to keep in mind is what's an episode. Okay, so we saw that in an episode, an agent starts from some initial state S0 and then does a loop for h minus 1 time. Okay, and so it observes okay, some state ST it's in, and then it chooses an action AT based on some policy. Okay, and then the environment responds to that by giving the agent a reward. So it gives a reward sample from the distribution R of ST AT. Okay, so this is from the reward function and moves on to the next state given by a transition function. So the transition function gives a distribution and you get a sample from that. Okay, and so the goal we discussed last time is to find a policy which is just a function from states to distribution of actions. And you're going to find the policy which maximizes its expected sum of reward, where the randomness is coming from the transition function, the reward function, and your policy. Okay, and I guess a comment here. Right. Uh, So this kind of program allows us to talk about, okay, what's the best policy, right? In the sense of maximizing the sum, but it doesn't allow it to as nicely reason about what's a good policy and a bad policy in the sense that there is no metric on this space, right? So we need to compare policies too. And for that, um, we're going to talk about value functions. Okay, so for a policy phi, which is a function from states to distribution of reactions, okay, we can define the state value function as this function from states to real numbers. The function is defined as expected value of sum over rewards, where you assume that you basically start from S at the H time. Okay, so more pictorially, you do some process and then your H levels states say that's S. Then the agent chooses AH from the policy pi applied to S. and gets a reward RH from the reward function. Okay, and then it transitions to SH plus 1 according to transition function. And then you choose AH plus 1. You get another reward, RH plus 1, and so on. Okay, until you reach SH. Okay, so value function is looking at the sum of these rewards. What's the expected value of the sum of rewards under policy 5? Okay, and another thing we'll need is this function called state action value function. Okay, it's also from a state times action to some real number. Okay, and this is just the expected value. Again, the same sum of rewards, but we start from S, and the first action is A. Okay, so we start from some state SH equal to S. We take action AH, which is equal to A. Okay, and we get some reward because of that. So that's the first randomness where we get the reward. And then we sample the next state and we continue the so AH plus this one is also just sampled from by S H plus 1 again, and so on. Okay, and so these functions, they're not adding any more value, but like they're kind of telling us how to compare different policies. So in the sense that now we can write our goal in terms of V values. Okay, so our goal is equivalently to find this policy which maximizes this VH by S0. Okay. Okay, I'm gonna just pause here if people have questions. But this is pretty basic RL stuff, so should be fine with anybody who has worked in RL. Okay, let's see if there are any questions.
Hi, are there any questions? Please raise your hand.
Oh, I have to set up the...
Nobody. Okay, thanks. I think everyone
Okay.
gets.
Okay, cool. Perfect. Actually, I cannot see the audience, so is that oh, that's probably not possible, right?
Yeah, so I think there's no audience camera, but there's a question.
Okay. Okay, perfect. All right, so
Gaurav, there's a question.
mhm.
Can you hear me?
Yeah.
Yeah, so my question is sometimes we also refer to something as a utility function. Is this the same as a value function?
Good question. I actually don't know. Is this utility function coming from like some other theory or in RL?
In RL, so like yesterday we had in lecture, so it was basically the expectation of the total reward. So that's how we are defining our value function as well, right?
Okay, so yeah, I guess if that's what you define, say utility function is exactly this. That's the value function starting from, I guess, S0, the initial state. I'm not sure if utility function is like, for bounded horizon or for like infinite horizon. I don't know what the definition of utility function is, but it sounds very similar. Um, okay. Sorry, did that answer your question? Okay, cool. So I'm gonna continue. Okay, so I'm just gonna make a small like notational simplicity. I'm gonna embed the horizon in the state definition. So, I'm just gonna ignore h. So my whatever I say v pi of h at s, I can just kind of just write it as v pi of s. So I'm just gonna just ignore the notation h for some time, and when it's relevant, I'll just bring it back in to kind of simplify things. Okay, so I can define the optimal policy. Okay, so we define v star of s as just the max over pi v pi of s. Okay, so that's just a function. I'm saying, these are the set of functions. Just look at maximum or supremum. Okay, and define q star of s comma a as max over pi q pi of s comma a. Okay, and I mean, say in the sense that these things are well defined, we said, the policy achieving these values is basically what we call optimal policy. So these are optimal value functions, and this policy which achieves this value is called the optimal policy. And I mean, I've done this in such an informal way, like why would max exist, So I mean, Q star and V star, they're like nicely even defined, right? And then, policy achieving these values might not even exist. So these are non-trivial questions, but people have worked out these things. And so, yeah, we know, like for the setup that I'm talking about, this policy, these max values will exist, right? Or like these will be supremums. And there will be like policies achieving them. And, the policies might not be unique. Okay, so that's true. These policy might not be unique. Okay, even though V star and Q star functions, right? They are unique. That makes sense, like, you're winning a chess game, the total V star value is gonna be like H, right? Like you win, all the time you win, or one, whatever, you can, some constant, right? And so V star is like fixed, but the policies which achieve optimal play might be many. Okay, and this is like the insight that's used in a lot of algorithms, is basically like instead of learning the optimal policy directly, you can learn V star and Q star S comma A as a proxy for learning. Optimal policy. Y star. Let's call it Y star. Some optimal policy, right? So uniqueness is kind of nice there. But also like representationally, they are basically the same, but it changes the optimization landscape. And that was very influential in, AlphaGo, and all these successes, where they were learning these Q and V functions. Okay, but we are not going to do that. We're going to do like direct policy optimization. So we don't need to like talk about V star, Q star functions, or learn V or Q values, even though we will for some other reasons, for variance reduction, stuff like that. but we will not need like access to V star or Q star or V or Q values. Okay, so we're gonna talk about policy gradient methods today. Okay, and basically how to code them. Okay, and policy gradient methods are used right now for, all these chat GPTs, for training chat GPTs and for playing games. So it's very modern, but it also has a very rich and long history. So, so the earliest kind of thing I know about this is the paper by Williams. So Williams in 1992 basically invented reinforce. So this is the vanilla policy gradient algorithm that I'm gonna do today, which is gonna solve Cartpole, right? So he introduced reinforce, and this algorithm uses policy gradient upgrade, this stochastic policy gradient update. And this is really the the workhorse for this algorithm. So how do you update the gradient? So this paper already like does everything you're gonna do today. Okay, but that was not the end, right? So after that, Sutton, McAllister, Singh, and Mansoor, they talked about the theory for policy gradient methods. Okay, so how do you analyze not like convergence and stuff like that, maybe, but what is this policy gradient upgrade? How does that change when you have when you want to do a policy gradient with function approximation? So this function approximation, this FAs. Okay, so yeah, so they were the ones which started kind of talking about the theory of policy gradient with function approximation. Okay, and then Konda and Tsiklis, sorry, I don't know if I said the name correctly. They came up with actor critic methods. Okay, and these are the methods which are used for playing chess and other games. These are very good methods. Okay, and then Kakade in 2001 in his thesis, talked about sample complexity and stuff like that, and introduced the natural policy gradient method. And then the modern kind of policy gradient methods came with Skolman in 2015 and 2017. Well, I guess also plus others. There was a lot of people. Sorry, and he came up with, and they came up with together PPO and TRPO. So yeah, these algorithms are used in ChatGPT 2 now. Okay, and so a lot of these like empirical papers but there's like lots of cool. So my interest is in the theory of RL. So there are actually lots of cool theoretical questions and also like open theoretical questions. In this area. So policy gradient methods, I think because they are so simple to describe and so simple to implement, their analysis, the theoretical design is kind of like a little bit tricky. So, but that, I mean, it's pretty cool area to work as a theorist. Okay, so let's talk about policy gradient methods. Okay, so what's the idea behind in general gradient-based methods, but like for policy gradient methods, is the idea of local improvement. Okay, so what's this idea? So recall our goal, right, is to solve this optimization problem. It's to maximize the value of a policy when you start from S0, find the best policy which in some sense maximizes this function, right? So S0 is fixed, it's actually a function of the policy, right? S0 is some fixed starting state, right? We just ignore that in some sense, right? Our goal is to maximize this. But let's talk about an easier problem, like somewhat easier problem, right? Suppose I give you a policy, pi, and I ask you like, can you make this policy better? You don't have to make it optimal, just make it a little bit better, can I update this policy from pi to pi prime such that v pi of S0 is strictly better. So v pi prime of S0 is strictly better than v pi of S0. So I don't want to like make it optimal, but I just want to improve the value. How can I do that? Can I solve this? And there is actually a very simple solution to this. If you move pi prime very slightly away from pi 0, so if there's a very small change from pi to pi prime, okay, then the first degree Taylor approximation just works, right? The only kind of information about your functional value, as you're going towards the point where you're asking for the functional value, right? It's going to become more entangled with the gradients, like lower order moments. So it's going to become third degree, second degree, and as you get closer to first degree, and then it's just going to depend on the function value, right? So this is the first degree Taylor approximation. You can write v pi prime S0 basically in terms of v pi S0, and then the gradient of v pi at S0. And this is a vector inner product with pi prime minus pi. So this is the first degree approximation, right? Okay, and this is just the gradient of v pi S0 with respect to policy parameters. Right, you have this function v pi S0, you're at pi, right? And to figure out what you need to do, you draw a tangent to the surface. It tells you what should be pi prime to increase v pi. Okay, and so really your update, if this is true, should be, make pi prime, so move pi prime in the direction of the gradient. Okay, so because if you do that, then pi prime minus pi is exactly the same vector. So your kind of value increases by norm of the gradient V pi all to norm squared. Okay. So this is great, okay, maybe the gradient could be 0, but like if things are all nice, right? And in some sense, like these shouldn't be 0, but the gradient should still exist always. It's non-trivial why, but it should. So you are always going to make improvement. So there's a very simple way to make small improvements. And basically, we can bootstrap this, okay, to design gradient-based algorithms. Okay, so there's a lot of questions like how to implement this. But today, basically, we're going to look at a simple gradient-based positive gradient method, okay, which basically iteratively applies this above strategy. Okay, and then we're just gonna, so it's gonna be a short thing, we're gonna just talk about the algorithm, and then we're gonna use it to solve Cartpole, which is, just a very classic control problem. And we're gonna use it to solve Pong, which is a really cool, Atari 2600 game. I mean, I never played on Atari. I played on like PC, but it's a fun game. It's a fun game. Okay, so that's the plan for today, and I'm just gonna dive right in, right? So what are the problems that we are trying to solve?
Audible?
Yeah.
I just had one question. How do you define the gradient of V with respect to pi? Like, what object is pi to really define this?
Yeah. So great question. And, we will come to that. So that's the, how you do compute that gradient, is really what, Williams did. So it's, it's slightly harder to grasp around.
No, but
But
how
are
do
you
you,
asking about the definitional problem or?
yeah, how do you even define this gradient? Because pi is some S to A map, right? Or maybe an S to distribution over A map.
Right. No, so V pi of S0
Hmm.
is just a number for a policy.
Oh, I see. I see.
Yeah.
All right. So it's just a vector then of probabilities and
So
stuff.
it's actually just a number. Yeah. So yeah, and then so you pick assign probabilities, however. So yeah, we're gonna talk about this. So but that yeah.
All right. Got it.
Right.
You.
Okay. Okay. So okay, why should we talk about Cartpole? So I think it's like really, really important to know about the problems that these algorithms are going to solve, because it's going to give you like some kind of intuitive understanding for like when do PG algorithms work, what are the problems for which policy gradient algorithms will work, and what are going to be like hard for RL. Okay, and just looking at the state spaces and their dimensions is also going to give you like a little bit like idea of like, oh, at this point, if my algorithm doesn't start working, then maybe there's some other issues. Okay, so let's look at Cartpole. So in Cartpole, you have a cart. Okay, and there's a pole hinged to the cart. So this is the pole, and this is the cart. Okay, and our objective is to basically prevent this pole which is, sitting on this cart. So it's hinged on this cart. Okay, from falling over. Okay, and the only kind of control you have on this problem, okay, is that the agent basically can apply a force towards the left or the right. Okay, and so you have to figure out when to apply force on the left and when to apply force on the right so that you can balance this pole. Okay, and this is like a hard physics problem. Okay, so let's look at what state space do we have for this problem. Okay, so the way you look at this, you go into the environment and you see what values it has. But basically, it allows you to access cart position. Okay, it's just going to be a real number. Okay, cart velocity. So how fast your car is moving. The angle that the pole makes with the cart. And pole's angular velocity. Okay, so state space is actually, continuous. Okay, so it's 4-dimensional space. And already this is like pretty hard for a lot of algorithms. If you have a continuous state space and you're using any kind of like tabular algorithms, you have to do some kind of covering and this is going to grow exponentially in the state space. So any kind of like continuous state spaces can be pretty hard in general for tabular methods. Okay, so already this problem, even though it seems a little bit simple, has the potential to be hard. Okay, but the action space is pretty chilled out. It's just there are two actions. 0 means, you pull left, and 1 means you pull right. Okay, so this is very simple, discrete state action space. So this is fine. Okay, another thing that kind of decides the complexity of the problem is a horizon. Okay, how long down the computational tree do you have to look down to figure out what's going to happen with the state? Okay, so in this case, basically it's like 500 steps. So it's basically coded up into the environment. If you move, whatever you do for like 500 steps, that's basically your episode. And then it ends, the episode ends. Okay, and episode also ends if your pole angle becomes too large. Okay, so it also has like kind of things for like pole angle. So there are constraints on the state space too, pole angle. And if it's too large, I think more than 48 degrees, you will see this in the code, but it's something around this. If it's too large, in absolute value. Or if like cart position is too off. Oh wait, I think cart position is probably like 4.8. Yeah, something like that. We'll see this number. Okay, then also this thing breaks. The episode ends and you start a new episode. Okay, and the implementation we're gonna use, that's gonna be from the gymnasium library. So gymnasium. and the name is like the Cartpole V1. Some of these things, I mean, it's just the code depends on which one you're like using. So, but these are all like pretty similar. Okay, so any questions about the Cartpole environment?
Yeah, there's one question.
Mhm. Sorry, is somebody asking a question?
Yeah, I think he's going to ask.
Hello,
Okay.
can you hear me?
Hello. Yeah.
Yeah, hi Gaurav. When you define the state space, the variables are dependent on each other in a way, right? I mean, when you say card position and the pole angle,
Hmm.
so they are not technically independent, right? But when you define a state space, the variables should be independent of each other, right? Technically.
Oh, no, yeah, nothing has to be independent of each other. It's just some like I like the state space is like R4.
But
So,
then we can define a state space which is a R3, right? Because the length of the pole is fixed. And if I have given the pole angle, I already know the pole position.
oh, you're asking like how many bits do you need to describe the state?
Yeah, technically. Yeah.
I mean, like I think what people really care about is like feature space. So you have like redundant information in general. So it doesn't affect any of the theory you're gonna do. Yeah.
Also, one more thing, like when we are saying pull left or pull right, we should also define the amount of force that we are putting, right? Because
Yeah. So the thing is like, you can make the problem harder by not allowing somebody to do that. So it's even a harder problem, this one. And like Cartpole is able to solve it. And this is like just a physics.
okay,
Cartpole is not like what I'm defining. It's the actual like define card like physics problem.
okay.
Yeah. So it's a pretty cool problem. Wait, I think I saw, let's see, there was a comment somewhere.
I think if you just bring your mouse down, you can probably see chat or somewhere, or maybe somebody else.
Okay.
I can try to find.
Oh, I think I figured it out. Nice.
I also have a question. So the
Mm.
horizon length, is it the number of switches from left and right that is done?
It's just time.
Oh, it's just time. Okay.
Yeah. Yeah.
Okay. Okay.
So it's like basically the h like like the t equal to 0 to h minus 1.
Yeah, yeah, yeah. Yeah, I get
H is 500. Yeah. Okay, why is V pi differentiable? Great question. We're gonna talk about like parametrization, so it's gonna be a big deal. What parameterization you choose is like hard. Like even in practice, it's hard like what to choose. And what you choose as the parameterization can and does affect sample complexity and computational complexity and like behavior of these algorithms. So in general, yeah, V pi, I mean, if you don't even define like, what pi is, it's not like differentiable doesn't make sense. But we're going to talk about parameterization. Dhanush, is there an assumption that the pole is falling because initial pole state could be steady? Yeah, so initial state is actually a random state here. You get it like something off centered. So the initial state is not like in a stable equilibrium. So yeah, it's like a physics thing, there's a place which is like an unstable equilibrium, and you kind of, if you add a little bit noise, it moves. Yeah, but I'm not going to get into the physics of this problem. But, solving this problem is requires access to, physics. So, okay. All questions done. I'm just going to move on to Pong now. Okay, so what is the game Pong? It is working. Okay. Okay, so this is Atari 2600 game. Okay, and the game is pretty simple. You have a screen. Okay, and you have two paddles. Okay, this is the paddle which is controlled by the game's built-in AI. Okay, and this is also another paddle that the agent controls. So that's what you control. Okay, and there is a ball. Okay, and so, it's like ping pong. The ball is moving, it goes to the left-hand side. If the AI will basically push it towards you. And the goal is to like not let it cross your side of the screen. Okay, so the objective, is to keep deflecting the ball away. Okay, and just put it into the open side. And the only control you have is to move the paddle up or down. Okay. And let's make this a little bit concrete. So, this is going to be 160 pixels. All right. And this length is going to be 210 pixels. Okay. Okay, so what does that mean for the state space, right? So basically in the game to the agent, what's present is just this, image of the game, right? So the state space here, it's so you get 3 channels, RGB. So you get 210, 163, right? So you get the for each color, you basically get the whole screen, and this is 160, this is 210, right? So you get this matrix, and then you get 3 matrices like this for each for R, G, and B channel. Okay, you get 3 matrices like that. So the number of parameters are like, the number of parameters in this matrix times 3. Okay, and this is just the state space is kind of like talking about just the image of game mode. Okay, and it's again continuous, obviously, in some sense. Okay, so I mean, this seems like already so hard, right? Like the state space before was like R to it's a 4-dimensional space. And now it's a much, much bigger, state space. Like even if it was like linear, it will take much, much longer time. Okay, and the action space is pretty chilled out even right now, So you have like discrete actions. You only have like 3 actions, 0, 1, 2. Okay, 0 means you do nothing. You stay in your place. Up means you go up, and down means you go down. Okay, so, every second is going to think sometimes, and you're going to figure out if you're going to move up or down or not move at all. And the horizon here is basically, when the ball goes through one of the opponent's thing, then the game ends. So horizon can be pretty large, but just the time proportional to like the game's memory. After that, it will just crash.
Hi, Gaurav. I have a question.
Yeah.
So sorry, what's the significance of the color information here? Why can't we just do white and black?
We can do just white and black.
I see. So that would reduce the space instead of 160 cross 3 to 160, I mean 210 cross 160 cross 2, right? So I mean, is there a significance to the RGB or?
Oh, yes. So it's these these are different colored. So this is I think green, I want to say.
I see.
Or so let's see. It's in my notes. So
I see.
I want to be very precise here.
So I have like a maybe follow up to that. So is it the case that the agent doesn't even know that there's a Pong game? Maybe the agent only sees these RGBs images.
Yeah, exactly, right? Yeah, that's exactly true. But the question is like, what is a Pong game? I guess Pong game is what like you need to know to win the game. Rest is all like random information.
Yeah, so maybe because you don't even tell the agent that there's a ball and these are the ball coordinates. Even that's not there. It's just like
Exactly. Yeah. So I mean, sorry.
No, I was saying this is, I guess, related to what Jatin was saying. You could simplify the game much more by just giving 3 positions on a 160 cross 210 grid, and telling the agent that it was two paddles and a ball. But here you're not doing that.
Yeah, I guess the goal is like not to make the problem simple. The goal is to make it hard and show that hard you can solve it.
Okay, thanks. Yeah.
Right. And so like the reason all these things were actually created is like as a baseline things your algorithm should be able to solve. And so when you write RL paper, the empirical paper, you go to like Atari set and you solve the big problems, like all the base ones, and people know which ones are hard. So, you should definitely solve this problem. But then there's like Monsuma's Revenge that used to be really hard. I think people have solved it now. I'm not sure. But yeah, that was like kind of like the hardest problem that existed for a long time. Maybe it's still not solved because I remember people using YouTube videos to solve it, like actual gameplay.
Okay, thank you.
Yeah. All right. So, but the game ends when any player kind of reaches. Wait, were there more questions?
not.
There is a chat.
Yeah, we can take them later also. You can just maybe finish. Yeah.
Yeah, okay. So any player reaches 21 points, then also, the game ends. Okay, and the implementation we're going to use is going to be the one from Arcade. So it's the Arcade learning environment. ALE. And it's the ALE Pong game. Okay, so the reason I'm giving all this information is because the code you write, like, so if you don't use this environment, the code I'm writing will not work. So it's just, there's some implementation details. Okay, perfect. So these are the two problems we want to solve. Okay, and if somebody asked like, how can you define gradients? So let's talk about that. Let's talk about policy parameterization. So, even before you talk about gradients and stuff, your goal is going to be you have a class of policies, right? The set of all policies is like it's continuous. So what you want to do is like you want to like parameterize it some way so you can search in that space. Okay, so let's see. We have a policy, right? It's just a function from states to distribution over actions. Okay, so let's make it more concrete, right? So what is a state for us? So in both the cases that I talked about, state was continuous. So, let's assume it's like RD, something continuous. Okay, and so for Cartpole, D was 4. And for Pong, D was 21, 163. Okay, and the actions, this is your 1, 2, okay. Okay, so for Cartpole, it's like K is equal to 2. K is equal to, yeah, right? Okay, and if you have this kind of like setup where the state space is continuous and actions are discrete, there's a very like simple policy parameterization that most people use. Is called the softmax policy. Okay, so what is softmax? So first we're gonna look at the parameters, right? So see. Okay, so for each action, so you're in a state, right? So you have a state is an RD, actions are K. So for each action, you have a vector that you store. Okay, and each of these vectors is in RD. So it's in the same space as the state space. Okay, so these are your parameters. Okay, so let's just, quickly count the number of parameters. All your algorithms, their complexity in some sense would be like dependent on the number of parameters. So the parameter counting is like very important in RL. So this uses, you have A actions, D parameters per vector. So A times D parameters. Okay. For our things, not so bad. For Cartpole, it's like, what, 8? That's nothing, right? Okay, and so, and the policy using these parameters is defined as follows. So, so policies, probability of taking action A in state S is exponential of theta A S. S here is vector in RD, right? You have a sum, all possible actions. Okay, maybe I should use prime here. Okay, so you can check the sum over all actions and pi theta A comma probability of A given S is 1. Okay, and all of these numbers are between 0 and 1. Okay, because all of these things are positive. Okay, perfect. Okay, so this is the parameterization we're gonna use. We're gonna store like these A vectors of D dimensions, and we can use it to define policy. And so now the value function is actually also differentiable in these thetas. Okay. Any questions about the parameterization?
So is it just an empirical fact that this is a good parameterization? We could have used many other parameterizations. It's, So
Yeah.
why this one?
That's yeah. So, it gets really complicated to analyze, like, what parameterizations are good. And so for example, if you pick your parameterization to be like tabular, you know, for each S comma A pair, you have a number written in a box, right? It's gonna improve the ability for you to compute gradients and for your algorithm to like provably go towards like optimal policy. All right, but it's gonna decrease your computational like ability. So it's gonna be much more computationally harder problem because you're storing more parameters. You're storing like, S times A parameters. If you're using a cover, it's gonna be like exponential sized cover. So, right. So
I see. I mean, I could just have used like a two-layer neural network or a few layer network for this, and maybe I would have had some hope that this was a complete basis of functions. But here we are not
yeah,
even trying to say that this is a complete basis, right? We are just saying this is a good
yeah.
basis to use it.
Yeah. So, people in practice use neural networks.
Okay.
Yeah. But okay, that said, there are like multiple papers. So there's a line of work showing that for all these baseline problems, basically linear policy works. So the one that I have written works.
Right.
And sometimes the optimization is actually faster on the linear one. The value you get, and like even the optimal policy is better with like linear. So they're very cool papers. Like Sham has papers on it, Sham Kakade and team, and Ben Recht has a really, really good. I mean, I think he's the one who probably started talking about it in the beginning. So, there are lots of good papers on this, like what parameterization you use, and we have theory papers on it. So,
okay, thank you.
Yeah. So let's talk about the algorithm. Okay. What we're kind of building towards. Okay, and there are problems. So what did we kind of talked about? We said like, if you're making small changes, then we can improve the policy by doing like this update. We go from theta to some alpha gradient of v by theta s0 with respect to theta. Just you change your parameters according to this gradient. And then you're going to make improvements. So if you kind of do this, maybe computationally it's going to be hard, but like information theoretically, this seems like it should be possible. Right? But the problem is like, in actually implementing this algorithmically is like, how do we compute this? Like, okay, I mean, yes, we know what pi theta is, we have some access to V. So we should be able to compute the gradient, but like, how do you actually achieve that?
Hi, Gaurav. We cannot see what you're writing.
Oh.
Something is strange.
Oh, it's not. Okay, let me stop screen sharing and reshare. Oh my God, how long has that been?
Not very long. Just a few
Okay,
seconds.
cool. Thank God. Okay.
Thanks.
So what have you guys seen? Have you seen the softmax policy paper?
Yeah, I think.
Okay, cool. Okay, cool. Awesome. All right. So I'm just gonna start with algorithm. Like in the algorithm, if you make small updates, this works. All right. The problem is like, how do you compute this gradient? Okay. And this was really like, what Williams did. So he showed that we cannot compute this, but we can compute an estimate. Basically, an unbiased estimator for this thing exists, right? Okay, and that's Williams. Okay, and he did this in his like reinforced paper. Okay, and there's a very simple strategy to building this estimate. All right, so you basically what you do, you run your algorithm, and you want to compute like the gradient in respect to some policy pi theta. So you run that policy. Okay, and when you run it, you observe, some randomness, right? So you're gonna observe S0, and then you're gonna choose the action randomly from pi theta, right? So you're gonna get A0. Based on that, you're gonna get some random reward R0. So it's like a random sequence, right? And so on, and you're gonna end up in the like last stage, and it's gonna end, right? Then you can use, this thing to create an unbiased estimator. Whoa. Sorry about that. Okay, and your gradient is basically the expected value. I mean, this is gonna look hideous, but it's like super simple. So let me just write it down, and then I can explain what's going on. Okay, it's a huge, but like just like what we're gonna do is gonna look at it like as parts, right? So the gradient of v pi theta is just the expected value of this function that I've kind of written down in terms of the trajectory. So this function just depends on the trajectory. And what's it doing? It's basically like computing gradient of the log of the probabilities and then just summing them up, right? Okay, so to compute this, you need like log probabilities of your action, whatever action you chose in whatever state. So you need this thing. And then you just sum it up. And then you scale it with like this sum of rewards. This is basically the return that you're trying to maximize. Okay, and so if if some actions are leading to good rewards, this basically pushes you in the gradient of the log of those things. So it's gonna just increase those. So it's a direction which increases the probability of actions, which increase reward, or the sum of rewards. So pretty intuitive. Yeah.
This term in the red square, the,
Mhm.
the constant term which is multiplied with every term in the outer summation.
Yes. So you can move it up.
Oh, okay.
Yeah. But so the reason I've written it, there is a reason. Yeah. But good observation. I think someone is paying attention, so I like it. Okay. So yes, like Jatin said, this term we can move it out. So why have you written inside, right? Is because you can actually replace this thing with other functions. And that's, a big part of designing algorithms in policy gain methods. So PPO, TRPO, they all look exactly like this in some sense, but there is like a different function instead of this thing. And so this function right now doesn't depend on, T. It's like basically does this whole sum. You could basically only start from, I'm just gonna make a small change. You start here from like whatever this T prime is. Or, make this T prime. But so you could do that. But there are other ways you can change it. You can make this value function. You can make this advantage function. So there's a lot of ways you can change this thing. And what really happens, okay, this is like a little bit informal. What really happens is like, you decrease like the variance of this estimator by changing these functions. And that improves the gradient method a little bit if you remove decrease the variance, but don't make it 0. And this is not like very formal, but empirically people have seen, it's basically some game of variance. You can do this to improve variance, and you get much, much better algorithms. Okay, so the kind of breaking like the suspense, but the algorithm I'm going to write today, which is going to be exactly this term that I've written, is going to work beautifully on Cartpole, but it's not going to be able to solve ping pong. All right, it's not going to be able to do that. It's because the state space has increased so much, right? But you replace this function with some other function like advantage, right? And it will solve Pong too. All right. So it kind of like really means, like these algorithms are really, really strong. So, and it's hard to like kind of guess why the algorithm is failing, Um, so it's a big game of variance reduction. And so there's lots and lots of papers on just improving this term. Okay, and lots of good things to try too, I think. Okay, so I'm just gonna write down the algorithm, and we are kind of like at the end of this thing. So in the algorithm, you initialize theta from 0. Okay, and then you do like this algorithm for some n steps where you run your policy by theta to obtain a trajectory. So S0, A0, start from starting state, pick an action from your pi theta policy randomly, and receive R0, S1, and so on. And then you compute your return, which is just the sum of your rewards. And then you update the theta using just the sum of your log probabilities. Okay, and so that's policy gradient. And so let's just quickly go into our PCs and let's just code it up real quick, and we can see how it works out. Because we have little time, I'm just gonna like go right into it. But if you have questions, just let's talk about questions while I'm doing that.
Yes, maybe we can take questions while you are loading the code. So I guess I have
Right.
a question. So are you going to prove at some point that what you wrote is actually an unbiased estimator of the gradient?
No, because I mean it's a you can look up this proof anywhere.
Standard.
It's a very easy, it's just a computation. It's a little bit tedious, but yeah, it's like 3 lines or 4 lines. But it's basically like you getting used to the notation. So I don't find it that insightful. Yeah.
Yeah, Gaurav, one more question.
Mhm.
I'm still not I still didn't catch it how the gradient of our v theta function is equal to the expectation of the log probabilities.
Oh yeah, that's exactly what Jatin asked. I haven't proved that, and it's a small proof. That's what Williams did. Um,
Isn't it simply that the expectation of, you differentiate p of x, f of x, and you get a derivative of p of x, which you can write as p log p, right? P of d log p. So it's just that, right?
Yeah,
I mean,
yeah, yeah.
you want to estimate the the
Yeah,
derivation
but
of the
I mean,
expectation, and that's the expectation of the log of the probability distribution.
yeah. And in general, what happens is like, there is gonna be like little bit of a term which is gonna be off. Right here, it's like pretty obvious.
Yeah.
But like, why is like why can you replace that with like advantage function or something like that? Those things. So the right proof is like looking at some kind of like tower sum there.
Okay.
Oh, yeah, but you're right. If you write the sum of like like a distribution,
Yeah.
and then you take the log, and you get the gradient of the log is like 1 over b. Yeah, but yeah, it doesn't. It's just math.
Okay. Okay.
Yeah. Okay, so let's code it up. Okay, how much time do I have? 4 minutes.
Yeah, but you can take after this also. You can take some more time. Maybe 4 plus 5 minutes, like 9 minutes. You can take.
All right, let's see. I mean, I'm restricted by my typing speed now. All right, so what I'm just gonna do is just start from the beginning. So let's see where I'm at. Okay, so what I usually do when I code any of these algorithms is I create a virtual environment because I have like messed up like my systems Python so many times. So it's just the easiest way. So I just create like a directory for my thing, RL tutorial.
So are you wanting to share a screen, or you?
Oh, wow. I'm not sharing screen, right? Okay, so I just create a thing and then, oh, you guys can see my terminal now, right?
Yeah, all good.
Okay, cool. All right, and then I think I'm assuming most of the people already did this. And if you do it once, it just very quickly. Right. And then you can just go into that. Okay, so now every command I run from this terminal, goes through this virtual environment. Okay, and I can just do upgrade because sometimes it has like old stuff.
I think there are two of those caches.
Thank you. Okay, then I install Torch. Okay, and that makes me ready to go. And let's do code. Okay, but now you guys won't be able to see this, so. Yeah, like Jupyter, so Cartpole. Kernel. Okay, and so okay, the first thing you're gonna do is just get these libraries, you're right? So this, so get the torch. Okay, so another thing you need is like how to build neural networks. All right, so So Torch has this library for building neural networks. You get that because not only do you want to just compute like with neural networks, right? You also want to do like this back propagation. So you want to also compute the gradients. And that's where like all these libraries are just really good. They're gonna just like save you so much time. Okay, and you need some optimizers to play around like with the neural networks, integrate them. So it computes the gradients, talks to the neural networks. All right, and in general, in this code, we're not going to use a scheduler. But if you're doing any kind of application, you would need a scheduler. Like otherwise, just using any kind of learning vector doesn't really work. Okay, and then you get gymnasium. I'll just write a gem. Okay, and this allows you to create environments, interact with them. But these two things are going to be like two different languages, right? In some sense, like Torch is going to talk about things in tensors, and Gymnasium is going to talk about like just the normal Python stuff. So you have to like do some layering to convert stuff from Gym coming out into a tensor. Okay, but that's going to come up later on. So the first thing we're going to do is just define our policy because that's the only thing we really need to do. Everything else is like pretty chilled out. Okay, and so we're not going to write the whole code by ourselves. We're just going to use the neural network module here. And that's going to allow us to like do back propagation for free. Okay, so I'm just going to just write the code. So here, what you're trying to say is like, I want to create a linear thing with like these many parameters. So dimension of the state space versus n times action space many parameters. So I'm just gonna create the base class.
Hi, Gaurav. Two things. I think firstly, people want to like zoom your screen a bit, zoom in so that people can read.
Oh, wow. Okay, so let's see. How do I make it full screen?
I think second is that I think we are running short on time. But we
Mhm.
take another 5 minutes, but like, yeah, I'm not sure if we can code the whole thing. 5 minutes.
Oh, that usually takes me like 10, 15, but maybe I should not. So let me go back to something else. That's a good point. Why do I do this, right? So I go,
Yeah, we can also just do it tomorrow. We can just do the code tomorrow morning. And I mean, and
no, yeah, it should be fine.
Yeah.
So let's do this.
Or maybe you could do like a part of it, like whatever you like.
Oh, yeah. I think I got it. So stop sharing so I can do this. Okay, I think my thing just broke. All right, okay, I'm back. So you can do. See. All right, I think we're in. Okay, I have a workaround for this, and
Hey,
that is
share your screen.
yeah. So I'm trying to reach my screen. All right. Okay. All right. So we're in. Do you guys see this? Oh, let me make it full.
Yeah, you can just make it zoom in. Thanks.
Okay. Right. So what I can do is just go over maybe the stuff from this is, yeah, it's okay.
Yeah, sure.
Maybe you guys already know how to code this, right? I think you already got this. So I guess the one thing I wanted to talk about this algorithm is, um, you do like this kind of like implementation where like you're implementing the forward code, right? And you don't have to really worry about how to compute gradients. And all that is like really happening through through the computational graph. And if you look at the computational graph, you can write the whole gradient using chain rule as like product of other gradients. So you can use the technology, all these linear functions I'm defining, like Torch already knows how to differentiate them. So it kind of like plugs them together to figure out the total gradient. Sorry, I had like another 30 minutes or maybe talk left. So maybe this is, I guess, over. But if people have any questions about the code, just ping me. Uh, uh, I like this code. So anyways.
Is this code on your GitHub?
So it's on the notes.
Okay. You mean the hard copy?
Yes. I mean,
Is there a note?
that's yeah. So I can also share the Jupyter notebook and the Python code. Okay, but what what I was gonna do was like actually just run this code and show you guys how the policy looks like and what happens when you change the variance thing and how the policy looks like. But unfortunately, I don't have time.
Are
But
you
I'll
sure?
share the code.
Yeah, sure. I mean, yeah. We can just do it tomorrow. Yeah, I think we have 2 hours,
Oh,
so I think there's no issue.
okay. I mean, yeah, we have lots of things to talk about. So yeah, I can do code tomorrow, and then we can do sample efficiency and also computation efficiency. And those are gonna be like super, or maybe not super like, but like a little bit like theoretical. So tomorrow is gonna be a little bit denser. Like I have been talking about a little bit implementation stuff, like, but I work in theory. So tomorrow and the after tomorrow is gonna be a little bit math. So I would need time there. So I don't know if I keep pushing things into the next day,
Yeah,
we'll eventually like, lose something. So maybe we can just I have to like think about it.
okay,
But
sure.
yeah,
Up to
yeah.
you. Up to you.
Okay, cool.
Okay.
But this is like, I love this code, so I'm sad, but maybe I should move on. I should look at what other people would benefit from too.
Okay.
Anyways.
Okay. Okay. So thanks, Gaurav. I will leave this mic here. I guess we will break for tea, and anybody can ask questions to Gaurav also now if they want to.
Oh, wait, somebody's asking how online participants can access. Can you tell us, please? Oh, there is, it's a public link. So let me share it to you. So this is the website where, this is on my homepage. I just have this page where I have uploaded all the lecture notes and all the details. So if you go to lecture notes, you should see the code and everything. But the lecture notes are not so current. Like I wrote them like a week ago, and then I've been like kind of doing a little bit like thinking on paper. So the lecture notes are not updated. Like what you're getting in here is this is the most recent. But lecture notes are written like a little bit slightly independently, but like they're also like they're more formal for sure. Okay. Any more questions?
Gaurav, I also have a question. Uh,
Yes.
so the state space for Pong, you had a
Mhm.
R to the 210 cross 160 cross 3, right?
Mhm.
It's shouldn't it just be 210 cross 160 cross 3 and not R to the this number? Because those are That is the
Like, I mean, it's just like a dimension, right? So how many real numbers are part of the state? They are, 210 times 160 times three many real numbers. And, those real numbers live in the space of like R to the, you know,
no. Why? Where is this real? The three are for the. Oh, I see.
oh, okay,
Yeah.
I think,
Oh, I get
yes.
it now.
I mean,
Yeah. I mean,
so
the colors. If it should be times 256 and not r to the this, I guess.
oh, yes, 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 yes. You're right. So you're saying like, things are not gonna be like arbitrary points, right? It's not gonna be like 1.66. It's gonna be like either 1, 2, 255. Is that your concern, right? You're saying it should be like
Uh,
one. Oh, so you cannot see. Sorry. It's like some number, like some set to the power 210 times 160 times 3, right?
yeah, I guess. Yeah.
Yeah, yeah, yeah. Yeah. I mean, it's just like the way I've
Yeah.
written the policy, it really doesn't like use that fact.
Huh.
Um, but you're right. So that's gonna be true for like, a lot of things, even for the Cartpole, right? Your computer has a precision. Nobody's working in actually continuous space.
Right.
So
Right. Right.
um
Yeah.
but yeah, I mean, all right, like some years ago, people were thinking like, there are actual constraints on your problem, right? It's not actually a real space. So you can use physics to figure out like a little bit of these, like add physics to neural networks. And I don't know if those things have worked. They have probably worked, but like, so they're like these general purpose policy grain methods, and then there's like physics helped PG methods, which kind of try to use that, what you're trying to say.
Yeah. Got it.
Yeah.
Thank
Sorry,
you.
what's your name? I haven't like, sorry, I should probably ask people to like say their name before they ask questions. Sorry.
I'm Nishant.
Okay. Hello, Nishant.
Hello. Hello. Yeah.
Okay. More questions?
I don't. I don't think so.
Okay. Okay, so I mean, there are more things I want to talk about. Like there's a lot of good theory problems, um, in the sense that we didn't, but like we would have just solved Cartpole using policy gradient, right? Solved in the sense that it's like kind of outputting really good policy, right? 500 is the maximum value, is going to output 500 like a lot of time. So how is it doing that theoretically? That is an open question. Like, can you even believe that? Like, we're gonna do this right now, like in 10 minutes, I would have coded it down and you would have solved it, but we don't understand theoretically why that is happening. I mean, obviously, like, we can probably solve it, um, but it's open. So, of all the PhD students who are here looking for an open problem, just pick this one and it can be solved. But they're like, I think a little bit tricks, but like this is like yeah, it's an open
Okay,
problem.
what is the open problem? Solving Cartpole using physics or something? What?
No, so I mean, like if you can solve Cartpole using physics. It's a classical like undergrad problem.
Yeah. So what is
Okay,
the?
so but why is policy gradient solving it? Like it's a gradient-based method. Why isn't it getting stuck on some, critical point?
Local optima. So
Yeah.
this other speaker, Eric, yesterday he was saying in the RL landscape there are only spurious optimas. Like every local optima is a global optima. So
Yeah, I mean, we only proved that for like few cases.
oh, I see. Oh, I see. Oh,
Yeah. So, I mean, like the cases we have proved are like nothing like this, like this is like continuous state space. So,
I see. Oh, I thought it was like in general in RL all the landscapes have like spurious.
no, no, no. I mean, I can create easily examples where this is not true.
I see. I see. Okay.
Yeah, because like, yeah. But like obviously, there's like I mean, it's a case of like parameterization. If you talk about like if you write in terms of just like tabular, or each probability is like just some s comma a number saved. Obviously, you can't do that for continuous, but like say it was like that, yeah, there's no local minima. So that's my first paper. That's the first thing I ever worked on.
I see. I see.
Yeah. But that's like simple, right? Like that's just like PL, like the yeah, there's like this condition in like gradient literature, like how proving gradient descent convergence is hard, but like there are like some PL techniques. You can use those things to bound, and it turns out to like super simple to prove that you can do that. But when you add function approximation, or you move from tabular to like even just normal softmax onto tabular, not even this linear thing, it's super non-trivial. It took me forever to like work that out. That is non-trivial.
I
And if
see.
you add linear function approximation on top of it, it's even harder.
So this is all in your first paper, is it?
So that was my first paper, yeah.
All right,
But nobody knows how to do linear, so like that is, yeah. So that is like a good question, I think. That's the question I was working on, like last time I was working on RL. uh, um,
all right, I'll leave the mic here if someone has.
yeah,
I'll go for
yeah.
it. Bye bye. Thank you.
Bye. All right. So I guess, are there any more questions?
I don't think so. The room is mostly empty.
Okay. All right. All right. Bye-bye, guys.
Bye bye.